Good evening. I'm Charles Schultz, and this is the Randomizer for the 21st of March, 2022. And tonight's subject is going to be one of those fundamentally simple terms that are very difficult to get across sometimes, polarity. So polarity is often known as having one of a couple of states that are in opposition to each other, such as the north and south pole of a magnet, or the plus and minus poles of a battery. Well, polarity literally means that, however many poles you have in opposite orientations. And many times it can be very difficult to explain the simplest terms because we have an intuitive feel, but not a very should I say, technical or exacting definition. We'll get into that very shortly. As you know, the randomizers, boy, this is a Monday, let me tell you, definitely. As you know, the randomizers happen at 6 p.m. Eastern Standard Time every weekday, and these are the shows where we pick a random technical term out of a hat. We've got over 1,600 entries and a random list, and the program whips one out, and that's the one I pick, and I run with it and talk about it. So you never know what's going to come out in one of the randomizers. Join us 6 p.m. Eastern Standard Time by clicking to the Schultz Laboratories or Universe Science Center site. Click through to the randomizer button and it'll automatically carry you to the page when the chat begins. It is a Zoom meeting format, so you are free to make comments, ask questions, and submit little suggestions or bits of information that we can all share live on the show. Also go to schultzlaboratories.com or universesciencecenter.com, visit our virtual world, see our educational material, our exhibits, interact with them, go in 3D, walk around and have fun with it. Bring your friends, get a lot of people to come and join us, support our efforts, become a member, and it will pay for more galleries, more content, and the ability to get this message out to more people all over the world. This is a great teaching and learning environment. For kids, they know exactly how to do it. They play games online all the time. They know exactly how to manipulate and walk through the environment. So if you're having a tough time, get an 8-year-old, they'll show you how to use the page. So now, back to polarity. This is one of those things that I'm going to try and make as simple as I can. And you know, our physical senses tell us many things about the world. And one of the things it shows us is that things tend to run downhill. And this is a very, very important part of explaining it. If you have a condition of high energy, it tends to run down to low energy. If you have high order, it tends to run down to lower order or disorder. And the reason for this is something we magically call entropy. And entropy simply means the running down or increase of disorder in any system. And it happens over time. And you could say, in a very real sense, that the arrow of time is in the direction that entropy increases. So every system that you work with, everything that you use, increases in entropy. And as to why, well, that's one of the great mysteries. But if you have any system that has order to it, over time, it will break down, it'll decay, it'll become more disorderly. And you know that this happens because things in the universe are transforming all the time. And this transformation is due to energy. And energy, what is energy? Energy is literally the catalyst for change. So anytime you have energy in a system, the energy is going to be doing its best to make things change. You can imagine having a ball up on a hill, and you push the ball, and it begins to roll down the hill. And it's going to release the energy that it has in that process. And polarity is almost as if you have a certain special type of hill, and when you put a bunch of things up on that hill, they're trying to shove their way back off the hill. Now, if you imagine all of space-time as being like pixels in a graphic image, tiny, tiny pixels of volume, and crammed together with enough complexity that the image they create of fields and matter and particles and all the things around you has such resolution they look like real, smooth, solid objects, then that's a pretty good native picture of what the pixels or the grains of space-time are like. But there's one other element to take into account, and that is these granules of space-time can be imagined as being connected to each other by rubber bands, and all of these pixels are stretched slightly, so there's a tension between everything. Everything is on bungees or springs, And when you disturb it, that wave of disturbance travels through the whole matrix of space-time. That's a pretty good picture that will give you kind of a gut feeling for what's happening when you tweak a particle in the array of reality and its waves travel off. Now, here's one of the tricks. For the most part, those chunks of energy or matter tend to remain as little chunks. But it can be, well, a little counterintuitive sometimes. Matter itself can act both as a particle or as a wave. And so this is how the disturbances move through the matrix of reality. And there's a matrix joke in there, I'm sure. So now, when we talk about polarity, when we look at a subject that has something like a hill that can be climbed, and you can look at a planet and an object in orbit around the planet, and if you stop the object, the pull of gravity will make it fall downhill. Now, that object has what's known as potential energy, and gravitation will move it in such a direction that the potential energy becomes actual linear energy, linear momentum. Kinetic energy is called. And when it strikes bottom, that energy can be released and converted into thermal energy. So energy can undergo different phases. It can be in potential form, it can be in an actual, such as heat, it can be as movement or rotation, and it can be waiting to be converted in these forms, potential energy. Springs, for example, are very good at holding potential energy, and a spring can be under tension. When you release the spring, what will happen? It will change its form, and the energy will be released as movement and as heat and possibly noise. Now, polarity tells us where these hills are. And when we talk about polarity, gravity only has one pole, and that's downhill. And it's possible for gravity to have another pole, but it would require some real tricks of physics that humanity hasn't quite figured out yet. When we talk about electrical current, we can see very clearly that plus charges represent an apparent hill, because when you try to pile a lot of things on, it's like stretching the spring, and the charges repel each other. Minus does exactly the same thing. But when you get the two together, there is a draw between the two to reach downhill. Now, there's an easy way to visualize this. When we talk about gravity, we often think of a flat rubber sheet, and planets or masses dimple the sheet in one direction. We can picture electricity as dimpling the sheets in two directions, some uphill and some downhill, and both of them want to reach the middle. So imagine one as being a spring being stretched, and the other a string being compressed. You can imagine the spring wants to reach neutral, somewhere in the middle. So you can stretch it or you can compress it, but it always wants to return to its neutral position. That's a pretty good way of positioning the image of plus and minus in electrical current. Now, we don't have a lot of things in our natural reaction with the universe that lay some of these terms out in a very clear manner. And one of the things that I like to do is explain, for instance, the phenomenon of electrical power and how it relates to a system of plumbing, for instance. If you had a system of plumbing, you would know that that system has water moving through it under some amount of pressure. And when you try to explain electricity as opposed to plumbing, one of the best and clearest examples you can give is this. Water in a pipe under low pressure can only move a little bit at a time through the pipe. The current through the pipe, the volume of water being moved, is controlled by how much pressure there is in the pipe. In an electrical circuit, an almost exact equivalent would be voltage. So when you say, well, voltage in a wire is equivalent to pressure in a water pipe, that's an image that we can see and we can understand. And understand that much of what we learn through analogy. So we have a model that we can see and it makes sense to us, and then we take something ethereal and invisible like electricity in a wire, and we can apply that model to it, and we can kind of get a feeling for what we're talking about. And that's what's important here. When we talk about polarity, we can imagine the flow in a pipe moving one direction or the other. And then we talk about AC current electrical signals that are alternating, we can imagine very easily the current traveling in this direction and that direction on a regular basis. And that's pretty easy to visualize. One thing that you can't do, though, in any model, there usually is a point where the analogy will break down. And for water in a pipe or electricity in a wire, that analogy breakdown occurs where you see arcing in an electrical system, but water or hydraulic systems can't arc. So polarity basically means you have more than one uphill position. And how does this work? Well, believe it or not, it's because the vacuum itself, the grid upon which the pixels of reality are written, is actually a material that has properties. It isn't just a nothingness. And there is a process called vacuum polarization. So when you have an electric charge here, an electric charge here, the vacuum between it is actually oriented in a special manner. How can that be? How can a nothingness have an orientation? It's actually pretty simple. What we think of as being nothing, as being the vacuum, is again literally a volume of uncounted trillions upon trillions of tiny volume pixels, each of which has the ability to store information. It's almost like a computing medium. And when we talk about nuclear physics and we get down to the details of the Planck scale, of the realm of the tiniest bits of space and time, we find that each of them has an apparent ability to store about 200 plus bits of digital information. If we start looking at the information stored in particles, the spin, the charge, the magnetic field, its mass, all of this as describing energy and how it is configured, suddenly it makes perfect sense. And the vacuum itself can literally be oriented in a special way. Now, this can be demonstrated by getting very close to a neutron star. As a neutron star rotates, it does a very strange thing to the vacuum around it. It polarizes it in the direction of rotation. It literally drags the space-time. So if you could stand there and drop an indicator, it would follow, just like a swirling whirlpool in the water, a stick will follow the direction of the whirlpool. If you have an object in orbit around a spinning black hole or a supermassive star, such as a neutron star, it will orbit more readily in the direction of spin of the star, and if you put it against the direction of spin, it will slow down and drop in and collapse. So the space, the vacuum itself around that star has been polarized in the direction of spin. This is called the Lense-Thirring effect. We can see it in numerous different media. So now this demonstrates that the vacuum itself can be polarized. Electricity and electrical fields do exactly the same thing to the vacuum. And this is one of the things that causes the conduction of electromagnetic waves, such as light and magnetic fields and radio waves and X-rays. All of these fields literally influence the vacuum, writing some information in there. Now, that information influences the passes of energy. Energy, as you know, can be configured in a couple of different ways. And as I mentioned earlier, we can actually think of energy as being the catalyst for change. And that makes a lot of sense. If you think of this grid of reality as tiny pixels of information bound together by springy little cords in between each, like strings or springs, then you get kind of a good picture of what physicists are having to model just to understand how particles and charges and movement all happen. So the vacuum itself isn't a nothingness. It's an extremely complicated structure. And as I've mentioned a few times in some of the other talks I've given, 1 cubic meter of space-time would contain something like 4 times 10 to the 105th power, 105 zeros, decimal places back there, of dots, quanta of reality, called Planck scale units. So that's an awful lot of information. And in fact, if you think about it, when you look at the scale of a human being, when you count the number of orders of magnitude to reach the scale of the sun versus the scale of an atom, you're closer to the size of the sun than you are to the size of an atom. if you took the big scale of octaves of tens, so to speak, orders of magnitude. So polarity is one of the properties that defines uphill and downhill for the two different charges of the electromagnetic field. And its explanation, the best way to put it is, in one of those dimensions, it's plus and minus for electric charge, and the other dimension, it's north and south for the magnetic field. The two are dependent on each other. So polarity, it is literally the different pole of uphill or downhill for a force. Now there's one fly in the ointment, and this is the trickiest one. When we talk about the strong nuclear force, on the scale inside the particles that make up the nucleus of an atom, the protons and the electrons, and all of their exchange particles, there isn't a bipolar force, it is actually a tripolar force. When physicists discovered this, they were kind of at a loss. You can't put a plus, a minus, and something else. So instead, they referred to the one other thing that the human sensory system can tell us, the color ring, with red, green, and blue being the three polarities of the nuclear force. Now, the interesting thing about this force, and it's called the chromodynamic force as a result of this, it has nothing to do with color, but those three poles were the only thing that they had they could easily represent that we could visually get a mental image on. So the red, green, and blue are the charges of the chromodynamic force, the strong nuclear force at the scales of quarks and nuclei. But over extended distances, this force tends to spread out until it becomes an almost bipolar force, and that's what we normally refer to as the strong nuclear force, or the nuclear barrier around the nucleus of an atom. So polarity, literally meaning the number of poles. For the strong nuclear force or chromodynamic force, it's a tripolar force, red, green, and blue. For electromagnetism, it is plus and minus for the charge aspect and north and south for the magnetic aspect. Curious fact, the weak nuclear force is almost identical to the electromagnetic force. It also has the plus and minus charge for the weak nuclear force, and it also has a north and south nuclear magnetic apparent force. So gravity, one pole, downhill. Weak nuclear and electromagnetic, bipolar forces. Strong nuclear force, tripolar. And that's about the best way I can sum up polarity for you. So if anybody has any questions, the floor is open. And meanwhile, I'm going to encourage you to go to schultzlaboratories.com or the universesciencecenter.com, visit our page, click through, become a member, and support the growth of our site, of our galleries, and the addition of new materials. And by the way, if you are an educator or you have a special skill or set of knowledge you want to share with people, get in touch with us and we'll set up a three-dimensional virtual gallery or classroom for you to use on our site. We want to get your message out there, share your skills and knowledge with everybody. So we have a little, okay, here we go. So a question on the floor, how does the vacuum relate to the spin of galaxies? All right, that's an excellent question. Galaxies' spin is controlled by the angular momentum of the cloud of dust and gas that it formed from. So if I have an object that is spinning, even if the pieces of it are distributed and they're all spinning by gravity around a common center, the average of those forces is going to give me a flat plane and a pole, the center of rotation and the pole of rotation. Our solar system is exactly the same in this effect. If everybody wonders why the planets all orbit in a plane around the sun, it's at the equator of the sun or very close to it, it's because all of the particles that our planets formed from were rotating in the same direction in that cloud. The sun is at the center of that mass and spins in roughly 33 days, 28 to 33 days, depending on what part of the sun, the pole or the equator you're looking at. Because it's a fluid, it can move at different rates. As it's spinning, its equator is the plane of the ecliptic, and all the planets were put together by all these colliding chunks of material, and the average of all of their motions is very close to the plane of the sun's rotation. The galaxy is exactly the same, but the reason solar systems are in different orientations in the galaxy is locally the clumps were moving in different directions because they resulted from the explosions of different stars, and the shock waves coming from those stars collapsed to make these clouds of dust and gas that, when cooled, started forming solar systems. And we have examples of these as nebulae all over our galaxy. And the best known local one is the Orion Nebula, where we can see the formation of stellar systems, stars and planets coming out of dust clouds right now. But in the scale of a galaxy, this happens not because the galaxy is rotating like the whirlpool in a stirred cup of coffee. Actually, it's counterintuitive. What you're really seeing in the arms of the galaxy is the shock waves of explosions and collapses of formation of new solar systems. So it's not spinning like a pinwheel. All the stars are rotating, but it moves almost as a solid. And that's what this is the other thing, the mystery of dark matter. We know that there's dark matter because it doesn't follow the faster spinning orbits in the middle and the slower ones on the outside. It's a nearly uniform movement because something massive like a halo is surrounding the galaxy and evening out that rotational force. So your question also leads to how we know about dark matter. And I hope that helped a little. Okay, and any other questions? Well, all right. Well, it's been an interesting talk, and there's much, much more to say, but I think I'll leave it at that. Look up polarity, and I'm going to read you my quote of the day. I love this one. And it is, for the commandments, you shall not commit adultery, you shall not murder, you shall not steal, you shall not bear false witness, you shall not covet. And if there is any other commandment, all are summed up in this saying, namely, you shall love your neighbor as yourself. And that's Romans 13:9. In other words, all of the commandments are subsumed in one super law. Love your neighbor as you love yourself. That makes a lot of sense. If only physics were as easy to simplify. Everybody, I'm Charles Schultz with the Randomizer, and I hope you've enjoyed tonight's talk. Have a wonderful evening, and as usual, make the world a better place. And thank you.